Hello, everyone. Thank you for joining. I'd like to introduce Dave Linder of Maplesoft. Uh, Dave's been working at Maplesoft quite some time in quite a great many different areas. He's going to introduce us to visualization, going beyond plot and Plot3d, sorry. Dave, take it away.
Thanks, Alan. Hi, everyone. So every now and then, I get a look at a few figures from marketing or Maple Primes or something, which talks about numbers of support requests, either numbers of error messages that get clicked through to the web, or tech support requests, or posts on Maple Primes, and plotting is by far the #1 thing in Maple that gets asked about. Something like 10 to 15% last time I looked of all queries and those kind of things turned out to be about plotting, not just ODEs and plotting, but plotting specifically. So it really does deserve its own attention. So today I'm just going to talk a little bit about the basics of how it works, and then some of the more fancy things you can do with it. Some of the things that aren't just the run-of-the-mill everyday commands. So first, I'm just going to do a quick overview of how it works. So Maple is composed of, a library of commands, interpreted library, and the kernel engine which runs those commands, and a few of its own commands, and then the graphical user interface, the GUI, or the command line interface. So what happens is that the library commands, they produce a plot structure. They programmatically assemble a plot structure, and then that's sent to the interface, which attempts to print them. The act of printing the plot structure is what makes it render the plot structure, or it's what makes it get sent to an external file. If the plot device is set to an external image format, then printing the plot would cause the interface to call its drivers to do that conversion. So you can create plot structures by calling plot commands and not displaying them, just by terminating with a full colon. But the act of constructing the plot structures is all library commands, and the plot structures are documented in the help system. And as you can imagine, we have a finite number of plotting commands, but there are more things that might want to do with plots than just those commands. You can't have a command for every single possible thing. So there's some manipulations of plots or combining of plots that sometimes go a little bit beyond what the basic commands do. So I'll talk a little bit of that as well. Anyway, that's out of the way. Let's talk about a simple one that comes up a lot, which is that, you have a command, but the result might always be your particular choice of look and feel. Sometimes we correct things or adjust the defaults. John may adjusted the defaults for contour plots, but there's some commands like density plot, which can have very, very different views according to what options you supply. One that came up a couple of times I've noticed is the dual axis plot. By default, you have two axes. One axis corresponds to the first plot, the other axis, vertical axis, corresponds to the other plot. But if they're both the same color, it's not immediately clear which one goes with which axis. These two axes are the same, but you could have different values on both axes, in which case you might want to know, how can I tell which one goes with which one? And a solution I really like for that is simply to supply options for the colors. So now we can see that the blue curve would go with the right vertical axis, and the red curve would go with the left one. And if these axis values were different, it would be very visually clear. But that's the kind of thing where everybody has their own choice of what they want to do to get the look and feel they like. I'm hoping that in future Maple might get some nice facilities for treating default plot behavior a little more nicely than just assigning to a variable and reusing it. but we'll see. So now on to a few special effects. For plots, I find that, the most important thing about a plot is probably the look and feel, and in particular, the color is a huge item. Maple's got some really, really nice facilities for doing color these days. And in particular, my favorite is the color scheme facility. This worksheet, by the way, is going to be available after the conference, so you don't need to take notes or anything, but you can run through all the examples yourself, or go through to click through all these help pages. The color scheme facility is actually quite extensive. There's all kinds of ways you can do it. You can do a color scheme, which is just a name, which gives you a particular color scheme. You can do a color scheme where you shade according to the Z height or the X value. You can do a value split so that a 2D plot or a contour plot or density plot gets color where the color changes by a particular value rather than just a relative position. There's a whole lot of choice there. So I'll just do a basic one. Here we have a density plot where I've got the color range is like a smear. It's like a blend of these three colors. The lowest values are blue, the highest values are red. When I look at this, I think it looks very nice, but I notice that the color gradient isn't very smooth. So there's something we can do about that. The RGB color scheme or color space is the default for many different kinds of plots, and it's the default for the color schemes as well. Now, RGB color space was originally designed for what your device emits. In other words, it's like a linear combination of the pixels on your computer and the way that the colors change is relative to how much light they emit. But that's not the way your eye works. Your eye perceives different colors to different degrees. It's more sensitive to some colors than others. And so a smooth gradient in the emitted light doesn't necessarily correspond to a smooth gradient in what you perceive. Fortunately, the color scheme, just like the color tools package, supports a whole bunch of different color spaces, two of which are perceptual color spaces, where a smooth gradient in the values of the color, numeric color values, will correspond to a smooth gradient in what you perceive. So I'll give you an example here. I'm going to use the LUV color scheme. It has to do a bit of work because it does some math there for every single point. But as you can see, now we have a really much smoother gradient between the colors. They perceptually blend in a very even manner, which is what we expected, because that's what this plot is going to do. So anyway, that's the kind of change that I feel is worth looking into. You can do a whole bunch of really, really powerful things with color scheme these days. So I've just given you a basic thing, but I feel it's one of those things where getting a little bit of practice with the color schemes can really make some of your contour plots and density plots really pop up. Okay, I'm going to go on to another example. Contour plots, surface plots, and density plots all have a relationship to each other. They all represent like the height or value of a bivariate expression. So in this example here, I've got an expression x and y, two plotting variables. I'm going to get a 3D surface from that. And often what people want is they want contours on this, or they want a 2D plot that's the same, but a density plot, or they want a 2D contour plot, or a 3D contour plot. And sometimes they want to put them all together. And sometimes people want them to have the same color, the exact same color. So you have a number of choices. You could recompute everything. And these days, most of the commands I've just mentioned also take the color scheme option. So you can simply supply the same color scheme option to all of those commands. But then you're recomputing. And perhaps you have a very expensive function, not just a very cheap one like sine of x times y squared. But if it was involved, say, complicated integrals, numeric integrals, and took 15 minutes to compute, you might not want to recompute all of those commands. So sometimes it's worthwhile to say, well, maybe I can convert one to the other just by doing manipulation of the data structure. A plot is a data structure which is actually just a nested set of function calls. The zeroth operand of the command of the data structure in this case in a 3D plot is Plot3d, all capitalized. And for a 2D plot, it's all caps plot. So we can actually take our data structure P and do a few simple programmatic manipulations to it and turn it into a 2D density plot. The colors match because all the data match. The values and the color data is all stored in that function call data structure. And so I can simply be guaranteed that I'm going to get all the same colors, all the same data, and they'll match. And I didn't have to do any recomputation at all. And now I've changed P in another way. Instead of being a surface, I've made it a surface which is a constant height, and I could choose whatever constant height I wanted. If I also wanted, I could use Plot Tools transform to transform XYZ to XY minus 1.1. But I've chosen to do it with a subsolve. A variety of different ways to accomplish the same goal. And I can now display them together. And this is a kind of plot for which there is no plotting command. There's no dedicated plotting command to get just this look. But I've seen it asked for maybe half a dozen times over the past couple of years. So it really, helps to be able to familiarize yourself with some of the techniques to combine plots in this way, manipulate them and combine them using plot display. I'm going to do another one. This is a contour plot now, where I've computed the contour plot myself with just the basic color equals black to get lines. And now I can transform the contour plot with black lines. I can transform it by raising all the black lines up to the heights of the surface. Or I can transform it by taking all the black lines and raising them up to the constant height of minus 1.1. I can then display those two with my original surface and my bottom density plot. And now I've got a density plot, which is smooth gradients of color, which is not the same as a filled contour plot, which is blocked color. I have the lines of a contour plot, a 2D contour plot, projected, and I have contours on my surface. And I didn't have to recompute all the values of the function at all the XY points. So that's nice because it's efficient, but it also gets me a plot that some people want. Now I'm going to do a patch contour. So I've recomputed a 3D contour plot. I've specified the contours and I've specified the color scheme. And now I'm going to turn that into a 2D density plot. Now I'm going to compute a contour plot, but I'm not going to fill it. I'm just going to compute the black lines. And I'm going to overlay them on top of the density plot. So usually when you do a filled contour plot, you get blocked color. The color is actually a whole bunch of very, very small contour quadrangles, but you don't see them because they don't have boundaries. But you do get block color. And you need the lines because otherwise you get fuzzy edges where the blocked colors change. Gradients of color in a density plot are smoothed by the GUI through interpolation on its part. And so now you get the lines of a 2D contour plot, but the smooth gradient of a density plot. And I can do a few tricks to that too. I can raise that up to a surface if I want, and I can put it all back together. So I've basically done the same thing as I did before, but with a slightly different set of techniques or set of steps to doing it. Are there any questions, by the way? If anybody wants to interrupt
We
me,
have
please.
we have one good question in the
Yeah.
chat. Said, is there a good way to go about learning how to manipulate the underlying plot structure?
Well, I have a talk coming up this afternoon for manipulating expressions in Maple. And as I just said, the plot structure is actually just a nested set of function calls. And so you can use the tools I'm going to be talking about this afternoon, things like subsindets and that kind of thing. You can use those to replace sub portions of a plot structure or act on them or get rid of them entirely. Suppose you wanted to take this plot and say get rid of all the lines. You could do that with one of those kind of commands. So I could talk a bit about that this afternoon if you'd like. How to otherwise learn? I think the idea is basically familiarize yourself with the structural tools for replacing and substituting into an expression, because a plot data structure is really just a compound expression. Familiarizing yourself with the type system and familiarizing yourself with tools like subsindets is a great way to go about it. I think here I've replaced something with subsop, so I've replaced something by position rather than by type. That's another thing I'm going to talk about this afternoon. And then here I've replaced something by type. So you can replace sub-expressions in the plot structure by type, or you can replace them by position, by operand position. So familiarizing yourself, I think, with those commands, which I'll be talking about this afternoon, I think is probably a good way to go about experimenting. Experimenting is really probably the best thing you can do, because the tools and techniques that you'll learn with replacing and substituting into plot structures are also going to help you for doing that with other kinds of Maple expression. I hope that's an okay answer for now. I'm going to talk a little bit about animation, because animation is one of those things where, again, it's very popular. It's a good visual effect that everybody enjoys. The usual ways to do plots animations are either to use the plots animate command or to use the plots display command on a list of static frames of plots and supply the in sequence equals true option. This basically just displays all of the plots in L in sequence, like an animation. In fact, this creates the same kind of data structure as does the plots animate command. But I got a couple of other choices here. So sometimes we have like a surface or an object in 3D, and we want to rotate it. And we'd like all the frames of our animation to be different views of this shape. It could be a surface, or it could be an ellipsoid or something like that. But traditional animations in Maple, the orientation is what's called a global plot option. It's just like the view is. You can only have one. The GUI goes through all the frames, figures out what the orientation is or what the view is, the biggest view, and then it sets that for all the frames. So if you want to rotate an object as your animation, you have really only two choices. You can do a lot of work in computation by transforming every frame, computing each frame by doing a transformation of like the original frame. So you have to do a mathematical construction of each of the frames by creating a new data structure for each frame by doing a rotation or a transformation. That's a lot of computation. It's also a lot of memory because every frame has exactly as much memory use as the first one. And so it's an expensive thing to send off to the GUI. So we have this viewpoint option instead. Now the viewpoint option allows for fancy stuff as well as simple stuff. I'm going to use the simple stuff where I just do the viewpoint which says circle left. I could do circle left, circle right, but I could also do like a fly through where your viewpoint can be a function in 3 variables with a position and an angle that you're looking at. So you can get some really amazing fly throughs where the view as it animates is to go sort of like you're in a spacecraft traveling through the ellipsoid. It's kind of fun. There's some good examples. But I'm just going to do this basic one. I got a knot, and now that's rotating. So it's circling left. And I only had to send the one plot structure to the GUI, and then the plot structure has the extra information inside it, which is basically a simple substructure that says viewpoint equals circle left. And that's the only extra thing I had to send to the GUI. So really cheap communication between the GUI and the kernel in plotting is something that, it's usually best to keep it down if you can, but animations are usually huge and expensive. So this kind of rotation is much, much cheaper than sending a whole bunch of rotated frames. And the last one I'm going to do is embedded components. So embedded components are available in Maple. Usually you can insert them with the palettes. You click on one of these buttons and it inserts a component, has a name, you can put code behind it and all kinds of stuff. But embedded components can also be programmatically constructed. The tabulate command is another type of embedding that's programmatic. So first I'll just do a embedding of a static plot. So each of these is a 3D plot. And I've put them in a table, which I've programmatically constructed. And I like this example because I think it looks fancy with the black background. You can also do a single plot and have a black background and a cyan set of axes or something fun like that. It's kind of dramatic, especially when there's a lot of color involved. But again, it's not something I see normally. A 3D plot can only really get a pure black background if it's done inside a plot component. So I thought, why not go whole hog and do the whole thing? I'm also going to do a fancy one where I've got 4 knots, and I'm going to create animations for each of the 4. I'm going to put all 4 of them in a table, and I'm going to embed the table, and I'm going to make it play all the plots automatically. So again, I think that's a pretty fancy effect. I don't see that too often, but I like the fact that you can write just one Maple procedure which creates these plots, puts them in embedded components with a black background, embeds them, and then sets them playing all at once. I'll just stop them for fun, but they act like regular animations once I've done that. And then Oh, another fun thing that I like doing with embedded components and animations. Um, uh, when you do an animation, the toolbar has all the controls for it. And if you have multiple animations that you want to play, you have to put the mouse focus back on each one separately, like I just did there, to stop them. So for fun, I have some code which puts an animation inside its own plot command, and then at the bottom, it has its own dedicated set of controls. So I can go to the beginning or to the end. I may have killed it because I've done a lot of GUI work in this session, so it's possible that. But essentially, these buttons normally they work exactly as you'd expect them to. You can loop, and you can this command I put it so you could actually tell it which of the buttons you want. So anyway, this code, the code for the black background stuff, the code for the viewpoint, and all of these things are actually going to be in the worksheet, and we'll have that available for download after the conference is over.